Hwacha. A wooden cart sits behind a Korean firing line. Its upper frame is packed with rows of long, narrow shafts, each carrying a small gunpowder motor. A soldier lights the fuses, and the cart does something that would have looked almost impossible in the 15th century. It starts throwing rocket arrows into the sky in rapid succession. This was the Hwacha, developed in Chosun, Korea, and paired with a rocket weapon called the Singijeon. Instead of asking one archer to launch one arrow, the Hwacha turned a cart into a firing rack. The Korean History Service records that King Munjong's version could carry 100 medium Singijeon, or a different rack of 50 small cannon tubes. With the Singijeon rack fitted, a single crew could send a mass of rocket-propelled arrows toward the same area. The arrow itself was doing two jobs. Its long shaft helped stabilize the weapon, while a powder-filled tube provided thrust. This was not a modern guided missile. The accuracy depended on construction, launch angle, weather, and the consistency of the propellant, but the Hwacha did not need every shot to hit the same point. Its value came from putting a large number of projectiles into the air quickly. That is why it looks oddly familiar from a distance. Put wheels under a rack of launchers and fire them in a group, and the silhouette starts to resemble a much later multiple rocket launcher. The technology underneath was completely different, but the battlefield logic already made sense. If individual rockets are imperfect, send enough of them toward the same area that the target has to deal with an entire patch of sky. Mysorean Rockets. 3 centuries later, British troops in southern India met a rocket that solved one of the old weapon's biggest problems with a piece of metal. Mysorean rocketeers used iron cylinders packed with gunpowder and attached them to long guide sticks, commonly bamboo. The stronger casing could tolerate more pressure than many earlier non-metal rocket bodies, which meant more useful thrust and range. The physics were straightforward. More pressure inside the combustion chamber meant the propellant gases could leave with greater force before the casing failed. Indian historical material describes this iron tube and bamboo arrangement, while the National Army Museum identifies iron-cased rockets as one of the notable weapons used by Tipu Sultan's forces. Hyder Ali and his son Tipu Sultan used these rockets during the Anglo-Mysore Wars. They were still unguided. A long stick could help keep one pointed generally forward, but generally was doing a lot of work. Rockets could arc, wobble, bounce, or come down at awkward angles. In a mass volley, however, noise, smoke, fire, and projectiles arriving across a broad area could disrupt troops even when the rockets were not precision weapons. After the fall of Seringapatam in 1799, captured Mysorean examples were sent to Britain. The Royal Artillery Museum notes that William Congreve's later system was inspired by the rockets the British had encountered in Mysore. Britain had spent years being shot at by iron-cased war rockets. Now it wanted a standardized version of its own. Congreve Rockets. William Congreve tried to turn the war rocket into a practical British artillery system. Congreve rockets came in different sizes and could carry explosive or incendiary payloads. They also kept the long guide stick that had become a defining feature of early military rockets. Compared with conventional artillery, a rocket launcher could be relatively simple and light. There was no heavy cannon barrel containing an explosion and directing the projectile. The rocket carried its own propellant and produced thrust in flight. That made the launching equipment easier to move, but it also meant the projectile kept accelerating after release. Small errors in balance, thrust, launch angle, or guide stick alignment could grow into very large misses. Britain used Congreve rockets in major operations, including the bombardment of Copenhagen in 1807. They could throw fire and explosives into a broad target area, but precision remained a problem. The National Army Museum records that British naval forces and Army gun and Congreve rocket batteries bombarded Copenhagen from September 2 to 5, causing civilian deaths and destroying buildings before the city surrendered. Waterloo produced an even better demonstration of the guidance problem. A National Army Museum account describes rockets climbing, turning nearly vertical, and in some cases coming back toward the British position. One apparently followed an observer before its shell exploded. That did not make the weapon useless. It made it better suited to area targets than precise ones. Early military rocketry kept running into the same lesson. Getting thrust was one problem. Getting repeatable flight was another. Prieur Rockets. By 1916, pilots were taking rockets into the air and bolting them onto fragile biplanes. The target was usually not another fighter, it was an observation balloon. Those balloons mattered because crews high above the battlefield could observe enemy movement and help direct artillery. They were also defended by anti-aircraft guns, machine guns, and fighters. The balloon itself was large. Reaching it safely was the hard part. The Prieur rocket tried to give pilots a better way to ignite these hydrogen-filled targets. On aircraft, such as the Newport 16, rockets sat in long tubes attached to the interplane struts. The RAF Historical Society records that a typical load was 6 or 8, fired electrically from the cockpit. A New Zealand museum account of a 1916 mission describes Newports carrying 8, 4 on each wing. There was no seeker and no guidance computer. The airplane was the aiming system. Early rockets were inaccurate enough that pilots had to fire from roughly 125 yards, which created the slightly ridiculous problem of needing to avoid the giant balloon immediately after attacking it. The RAF source notes that pilots sometimes had to make steep post-firing maneuvers to prevent a collision. Prieur rockets found some success against tethered observation balloons, but not against airships, and incendiary ammunition soon offered a better answer. For a short stretch of the First World War, though, pilots really did fly into anti-aircraft fire with bundles of rockets fixed to their wing struts, aim by pointing the whole airplane, fire at close range, and then turn away from the enormous burning object in front of them. Great Panjandrum. During the Second World War, British engineers tested a demolition weapon that looked like 2 giant wheels joined by an axle and surrounded by rockets. It was called the Great Panjandrum. The concept was a rocket-propelled demolition device for amphibious operations. Instead of using an engine and drivetrain, designers attached rocket motors around the rims. Fire the rockets, spin the wheels, and the machine should roll itself across a beach, carrying a destructive charge toward an obstacle. Imperial War Museums preserves 1944 film of the trials. The beach footage is what turns an odd concept into something unforgettable. In one trial, a 3-rim version starts from a ramp, rolls along the beach, tips over, and crashes. Rockets break loose and skitter away. A dog named Aminal chases stray rockets. Later versions use 2 rims. Engineers add cables to steer the machine. In one test, it veers toward the camera. In another, a control cable snaps and flicks over the operators. The propulsion worked well enough to make a huge wheel move. Control was the problem. The thrust came from multiple small motors mounted around rotating rims while the wheels were bouncing across uneven ground. One motor behaving differently, one rocket coming loose, one wheel digging into softer sand, or one steering cable pulling harder could change the direction of the whole machine. The IWM record is a catalog of beach trials, not a combat history. What survived is the experiment itself. Engineers trying to solve demolition on a defended shore by putting rockets on an enormous wheel, then repeatedly discovering that the wheel had its own ideas about navigation. Bachem Ba 349 Natter. Germany's Bachem Ba 349 Natter took the phrase rocket interceptor almost literally. Late in the Second World War, Germany needed a cheap way to attack Allied bomber formations. The Natter was built largely from wood, launched vertically from a tower, and driven upward by a liquid-fueled rocket motor assisted by 4 solid boosters. The Smithsonian describes it as the world's first manned vertical takeoff interceptor. Then the pilot was supposed to fire rockets from the rocket aircraft. Ground control and an autopilot would handle much of the climb. Near a bomber formation, the pilot would take over, jettison the nose cover, point the aircraft at the target area, and fire all 24 Henschel H's 217 Phone unguided rockets from the nose. With fuel nearly exhausted, he would descend and separate the nose section. A parachute from the rear fuselage was supposed to decelerate the aircraft and throw the unstrapped pilot free so he could open his own parachute. The valuable rocket motor could descend separately for recovery. Much of the wooden airframe was expendable. The system reached flight testing, but its first manned vertical launch ended catastrophically. Test pilot Lothar Sieber was killed after the aircraft went out of control and crashed. The Smithsonian notes a possible canopy problem, but says no cause was determined. 10 Natters were later positioned near Stuttgart, yet the war ended before the type saw combat. So the proposed combat sequence was this: launch a man vertically on 5 rocket motors, let him close on a bomber formation, expose a battery of smaller rockets in the nose, fire all of them in one salvo, then split the aircraft apart and bring the pilot and engine down on separate parachutes. Germany never got the chance to find out whether that full sequence could work in combat. Tiny Tim, American aircraft designers had a different rocket problem. Sometimes the target was so tough that the answer was simply to make the rocket enormous. Tiny Tim was the result, and the name was not serious. The U.S. Navy weapon used an 11.75-inch rocket body with a standard 500-pound semi-armor-piercing bomb as its head. A wartime Navy damage report lists the assembled round at 123 inches long and 1,288 pounds. That is more than 10 feet of rocket weighing well over half a ton. Its size created an unusual launch problem. Igniting that motor directly beneath an aircraft risked damaging the plane with the exhaust blast. The solution was to release the weapon first and ignite it after it had dropped clear, using a lanyard arrangement. Tiny Tim was less a normal wing rocket than a bomb-sized object that had to fall away from the aircraft before becoming a rocket. The weapon arrived very late in the Second World War. USS Franklin had Tiny Tims loaded aboard when Japanese bombs devastated the carrier in March 1945. During the fires, some rocket motors ignited. Navy records and survivor testimony describe weapons propelling themselves across or off the ship amid the secondary explosions. Tiny Tim's wartime use was limited, but the type survived long enough to appear in Korea, where Sky Raiders carried 11.5-inch Tiny Tims with 500-pound warheads in an unsuccessful attack on the Hwacha Dam in April 1951. The weapon began with a straightforward request for more punch. It ended with pilots carrying a 10-foot, half-ton rocket so powerful that the safest firing procedure was to drop it like a bomb first and only then turn on the rocket motor. Air to Genie. In the 1950s, the United States faced an ugly air defense problem. A formation of Soviet bombers might be carrying nuclear weapons, and interceptors needed a way to stop several aircraft quickly. One answer was an unguided rocket with a nuclear warhead. The AIR-2 Genie had no guidance system. It was a solid propellant air-to-air rocket designed to be fired at bomber formations. The lack of a seeker was not an oversight. The nuclear warhead gave the weapon a destructive radius large enough that a direct hit was unnecessary. The Genie entered operational service in January 1957 and was carried by interceptors including the F-89J, F-101B, and F-106A. Thousands were built. And once, the United States fired a real nuclear-armed Genie. On July 19, 1957, an F-89J launched one at 18,000 feet over Yucca Flats in Nevada. The warhead detonated in the air. According to the National Museum of the United States Air Force, it was the first and only test detonation of a U.S. nuclear-tipped air-to-air rocket. The design solved the accuracy problem in a very Cold War way. A conventional unguided rocket had to pass close enough to damage one aircraft. A nuclear rocket only had to reach the correct volume of sky. The result was an operational air-to-air weapon built without guidance because its payload made a near-miss part of the plan. ASROC Sindida. The U.S. Navy then used rockets to solve a problem in the opposite direction. Instead of attacking aircraft above the fleet, ASROC was designed to attack submarines hidden below the sea. A surface ship might detect a submarine with sonar, but still be too far away to use a conventional short-range anti-submarine weapon directly. ASROC, short for Anti-Submarine Rocket, acted as a fast delivery system. A rocket-powered airframe carried a homing torpedo or a depth-charge payload toward the target area. In June 1960, USS Norfolk fired an RUR-5 ASROC during the weapons evaluation period off Key West, and Navy records from the same trials show the launcher and the rocket being prepared aboard the ship. In the torpedo version, the point was not for the rocket itself to chase the submarine underwater. The rocket crossed the air quickly, delivered the torpedo near the contact, and let the torpedo take over in the water. Cold War ASROC could get stranger still. Naval History and Heritage Command records that the system could deliver a nuclear depth charge, part of the Navy's effort to fight Soviet submarines in a possible nuclear war. NAHC also notes that one U.S. ship conducted a live nuclear ASROC firing. The engineering logic was perfectly reasonable. Air and water reward different propulsion systems. Rather than force one weapon to be good at both, ASROC changed modes during the attack. It left the ship as a rocket because the fastest route to the target area was through the air. Then it stopped being a rocket because the final fight was underwater. Gyrojet. By the mid-1960s, engineers at MB Associates had taken the rocket concept down to handgun size. The Gyrojet pistol did not fire a conventional cartridge with a bullet pushed down the barrel by expanding gas. It fired a miniature rocket. A 6-shot pistol could therefore look roughly like a normal sidearm, while every projectile in its magazine carried its own little motor. Smithsonian collections preserve Gyrojet rocket pistols and 13mm rocket cartridges from the period. The firing mechanism was almost backward. The patent describes a hammer that drives the rocket rearward onto a fixed firing pin. The primer ignites the propellant. As thrust builds, the rocket moves forward, pushes the hammer back into the cocked position, travels through the barrel, and leaves under its own power. There is no normal empty cartridge case to extract. The ammunition added another strange feature. Angled exhaust ports spun the projectile for stability, so the barrel did not need conventional rifling to do that job. And unlike an ordinary bullet, which receives almost all of its acceleration before leaving the muzzle, the Gyrojet kept accelerating in flight. That meant its velocity was unusually low right at the muzzle and increased farther down range. Contemporary descriptions of the system note exactly this odd behavior. That was clever, but it created practical problems. Very close to the muzzle, the rocket had not had much time to accelerate. Accuracy and ammunition consistency also limited the system. The rocket pistol reached the market, but it never replaced the conventional handgun. And that is where this whole history ends up. The Hwacha dealt with imperfect rockets by launching 100. Mysore strengthened the motor casing. Congreve standardized the weapon and still watched some fly the wrong way. First World War pilots aimed rockets by steering an entire airplane. Cold War engineers used a nuclear blast radius to make precision less important. Gyrojet went the other direction and shrank the rocket until one person could carry 6 of them in a pistol. It worked. It just did not work well enough to replace the ordinary bullet. The boring old cartridge stayed cheap, compact, and effective, while the rocket pistol became a museum piece. Which is exactly why it belongs here.